The next topic we're going to look at is torque. And torque is the rotational equivalent of force. We already know Newton's second law is F equals ma. Newton's rotational second law is that torque equals I alpha. So since torque is the angular equivalent of force, we insert the angular equivalent of mass and the angular equivalent of acceleration. So that's the Greek letter tau. It stands for torque, and yeah, I'll talk a little bit more about the units and so forth in a minute. So just like a force causes an acceleration, a torque is what causes an angular acceleration. And just as with Newton's second law, we know this is a net force, or maybe sum of the forces. This is also a sum of the torques. Right? You already actually know something about torque. You may not have ever really thought about it, but whenever you have a door, you know, the door knob is here, while the hinges are over here. That's because the amount of torque is proportional to the distance from the pivot where a force is being applied. It's related to force. It's also related to how far that force is acting from the pivot. I don't know if you've ever tried, but if you, say, push on a door right near the hinges, it takes a lot more oomph to get the door to open or close as fast as you would if you push on the outside. So next time you're going to a door, try to open it by pushing right near the hinges, and people will laugh at you, but you'll learn something about torque. All right, so torque is proportional to radius. It's also proportional to the force being applied. It's also related to an angle, and you kind of subconsciously know this too. When you go to open a door, you know, you push it perpendicular to the door. You don't push toward the hinge because you know that's not going to move the door anywhere. So torque is also related, well, to a trig function. It is sine because sine has its maximum when the angle between the force and what's called the lever arm is 90 degrees, and it's 0 when the angle between the force and the lever arm is 0 degrees. So it's also proportional to sine of theta, and theta is between the force and the lever arm. For most things, it's obvious what the lever arm is, or maybe not obvious if I asked you what the lever arm is, but it's kind of intuitive as to what you need to push perpendicular to. You push perpendicular to the door. The lever arm is just kind of an imaginary line from the pivot point to where you're applying the force. So that's how you can think of lever arm. So putting this relationship together, torque, for those of you who know this, I'll just throw this up here real quick. Torque is equal to force. It's the cross product of force and radius, which if you've dealt with cross products, you know what that means. But what you need to know is that it's force times the sine of theta times the radius will get you the magnitude. Torque also has a direction. Pretty much a torque can be clockwise or counterclockwise. You know, obviously, if you apply force in a certain way, the door will swing open. If you apply force in the other direction, the door will swing shut. And you can figure that out just by looking at where the force is relative to the pivot point. Say I have a rod. It's just chilling out here, and we always identify the axis of rotation with a little x. Oh, that's out of your screen. I apologize. We identify the axis of rotation with a little x. If we apply a force over here, well, this will cause the rod to spin that way. And that way is, I always have to think about it, that way is counterclockwise. So force 1 causes a torque in the counterclockwise direction. If I apply a force over here, say force 2, well, that will cause the rod to spin in the other direction. that direction is clockwise, so that second torque is in the clockwise direction. So you can see the torques can be in different directions. Now, a force over here, F3, even though this force is pointing in the same direction as force 1, because it's on the other side of the pivot point, you can see it would cause the rod to spin in the opposite direction. That's also clockwise. So even though two forces point in the same direction, they can cause torques in the opposite direction. Likewise, forces 2 and 3 are in opposite directions, but then they cause torque in the same rotational direction. So torque's kind of goofy like that. If F1 and F3 were equal, the net torque acting on this rod could be 0, but then the net force might not be 0. Whereas if F2 and F3 were equal, the net force might be 0, but the net torque might not be. So those kind of weird situations can happen. A net torque of 0 means an angular acceleration is 0. The rotational motion of the object isn't changing. And we already know a net force being 0 means the acceleration is 0, which means that the linear or translational motion of the object is not changing. Bet you all didn't expect this event to have costume changes. I just went to volleyball practice and came back. Anyway, so I just wanted to talk briefly about what's called the right-hand rule. When we're talking about torques, it's pretty arbitrary. It's just a convention that we use, but it becomes very important when we're talking about electricity and magnetism. So I'm going to go ahead and teach you guys now. So if a torque is pointing in the counterclockwise direction, if it's going around this way, then the way we state that the direction of that torque in physics is by following what we call the right-hand rule. The torque is going around this way, so we curl our fingers, the fingers of our right hand, in the direction of that torque, and then the direction your thumb is pointing when you do thumbs up is the direction of the torque. So a counterclockwise torque, by the right-hand rule, the direction my thumb is pointing is out of the board. So we say that is coming out of the board, or on a test, that would be out of the page. And likewise, a clockwise torque, well, that'd be pointing the other direction. So if we curl our right hand in the direction of that torque, which is easier to do from over here, curl our fingers in the direction of that torque, our thumb is pointing into the board. So instead of saying the torque is so many Newton meters into the page or out of the page, so many Newton meters clockwise or counterclockwise, we're going to give the directions based on whether they're going into the board or out of the board. The same is true of an angular acceleration or velocity. Whatever direction it's going, you curl your fingers in the direction of rotation, and then your thumb points in the direction of whatever quantity it is we're talking about. Right? So let's look at an example. All right, let's say we have this rod, and it has an axis of rotation that goes through its center. Let's say this rod is 12 centimeters long, and let's say we have two forces acting on the rod, F1 and F2. F2 has a magnitude of 11 newtons. F1 is a magnitude of 15 newtons. F2 is acting 5 centimeters from the axis of rotation. F1 is acting 3 centimeters from the axis of rotation. And the whole rod has a mass of 1.1 kilograms. And I want you to find angular acceleration. All right, well, we just need to add up the torques. We know the sum of the torques equals I alpha. So we just add up our torques. Both of these forces are acting perpendicular to the rod. So we have F1, 15 newtons, times the sine of theta, but theta is 90, so the sine of theta is just 1, times the distance from our pivot point, which is 0.03 centimeters. Now this force is providing, the torque is 11 newtons times the lever arm 0.05, but they're in opposite directions. We're going to call the out of the board or out of the page direction positive, and we're going to call the into the board or the page direction negative. So this force would produce a torque in the counterclockwise direction, which is out of the page. So that will be a positive torque. This one is producing a torque that goes into the board of the page, so we're going to call that negative. Then, looking at our handy-dandy chart, a long rod axis through the midpoint. The moment of inertia is 1/2 m times L squared times our angular acceleration. And then you could figure out the magnitude of, figure out what your angular acceleration is. Now, if we punch this into our calculator, it's minus 15 times 0.03 plus 11 times 0.05 divided by 0.5 times 1.1 times 0.12 squared. That comes out to 12.626262, whatever, which rounds to 13 radian per second squared. Since that is a positive number, that means it is counterclockwise, so we say that it's 13 radians per second squared out of the board. Now let's take one more example here. Here we've got two people on a teeter-totter. This person has a mass of 85 kilograms. This person has a mass of 62 kilograms. This teeter-totter is 5 meters long, and we'll say that the fulcrum is where the teeter-totter rotates around, is halfway down, so that's 2.5 meters from the middle to the end. And we're going to say the only force acting here is gravity. So if we want to find the torque, well, our first torque is going to be, well, the torque is just force times radius, so that's force 1 times radius 1. This force is mass 1 times gravity. I'm sorry, this should say force 1 times sine theta 1 times sine theta 1 times radius. So this torque is the mass, 85 kilograms, gravity times 9.8 times the sine. Now here's the part where this is tricky. The sine of it is not 11 degrees because the sine, this theta, is the angle between the force and the lever arm, right? And the lever arm is the beam, so we're looking for this angle. Since gravity is straight down, if this is 11 degrees, this angle must be the complement of 11. So this is actually the sine of 79 degrees times 2.5. Then our second torque, similarly, 65 times 9.8 times the sine of 79 times 2.5. This is down, which means it'll cause the teeter-totter to rotate this way. Curl our fingers in that direction, thumbs pointing out of the board. That's positive. Opposite way, thumbs pointing into the board. That is negative. So our total torque would just be the sum of those two.